for these examples, the constraint is minimum of 2 groups, maximum of 3 groups, and have once OH functional groups. Okay, if you look at here, this is what we generate. Okay, so based on the ordinary macchiato, they have a 5 equation that you have to follow to screening these molecular candidates. Okay, so first equations regarding on the, where is it? And this one is on the have a valence group and also have a number of groups. Okay, and so on. So we will see the examples. I will explain very, maybe if you not don't understand, you can ask about this one. This one is important for the generation of the molecules. Okay. So based on previous examples, we call it the examples. Okay, given the group of CH3, CH2, and OH, so we have to generate molecules. So since U is what is it, U valence group, right? So if you look at here, that valence group is for CH3 is 1. Okay, CH3 is 1. Of course, we can attach with the one functional group, so meaning that only 1. Okay, CH2 definitely 2, OH is definitely 1. And just remember, generally for the lower n is what? This one what? NGL, right? Okay. NGL is a lower bound. Okay, generally is 0. And then upper bounds is the number of maximum that you can put in the group. For CH3, maximum is 2. There is now CH3, CH3, CH3. Okay. So it's I think its maximum is 2 lah. Okay, if CH3, CH3, and there's no CH3, CH3, CH3. Okay, so CH3, CH3, CH2, CH3. CH2 can be 2. CH3, CH2, CH2. Oh yes. So maximum is 2. Okay. For OH is already mentioned, only 1. So maximum number is 3. We want to generate acyclic. Okay, number 1. So we have to 1 lah, right 1. Okay. And then maximum number of molecules that we can generate is 3. Okay. So if you look at here, that previously I already explained, maybe it's too fast. Okay, I can explain a little bit slow lah. This one. So if you look at here, that this one CH3 vector group, 2 CH3. Okay, 2 CH3. Okay, and then a number of group present here, 2 lah, 2 CH3. So we just write 2. Q because acyclic, right? All this one is 1. Okay, 1. Okay. So based on the equation number 1, this one is equation number 1, 2, 3, 4, 5, right? So this one is number of valence. CH3 have number one valence, right? Because only can one atom or one molecule can attach to CH3. Like this one is CH3 and CH3. Okay, and J is this one. And J is what we call it as a number of groups present. This one only CH3, so they have a 2 CH3. So right here 2 CH3. 2 times with Q is equal to 1. Okay, so 2 times with Q 2. So it meaning that 2 minus 1 times with 2 is equal to 2. Okay. Okay, rule number 2. Okay, question number 2. If you look at here, that's not applicable. Why? Because it should be have Ni and Nj. This one we have only Ni or Nj only, so it's not applicable. There, for rule number 3, it should be have a two groups, 2 vector group like this one, like CH3 and COH. That's why we can use this one. This is not applicable. Similarly, also for OH. Okay. So for the Nj, U and NJL, this one upper bound, lower bound, as I told you that lower bonds we set as a 0 generally, and upper bound is maximum only 2 for CH3. We see the previous tables, okay, the previous slide. And then Nj, 2 lah, this one present. We have 2 Nj, this one, right? So we just write 2. So between 0, 2, and 2. How about this one, NJ? And max, we said all is 3, right? This one is 3. Okay, because that is all and max. NJ, of course, is 2 lah. NJ below than N and max. Okay, and then N is equal to N NJ, meaning that totals we have 2. Okay, this one is easy. Okay, okay. So the red, not the red one. Second one is CH3 and OH. Okay, so one CH3, one OH. So number of groups we have 2 lah. This one true. If this one we have 3. Okay, 3. So we have to calculate rule number 1. If you look at it, valence 1 for CH3, valence 1 for CH, and for OH. And number of group is this one is equal to 1, this one is equal to 1. Because CH3 1, OH 1. Okay, equal to 2. 2 times with 1. Okay, because Q is equal to 1. Okay. And then rule number 2, we set J as equal to CH3 and I is equal to OH. So meaning that Ni is equal to 1 lah, because OH is equal to 1. Okay. And then Nj is equal to 1. U is a what is it? Number of valence group. Number of valence group is only 1, right? Uj is a valence group lah. Okay. So 1 minus 2 times with 2. This is from the equation. Similarly, also you do for OH. So we can get actually is Ni is equal or more than 1. Okay, this one 1 minus 2 0. Okay. 1 minus 2 is negative 1 times 1 negative 1 lah. Negative 1 plus 2 equal to 1. 1. Okay. So equal or more than 1. Okay. And do the same thing for rule number 3. Okay. OH is 1 maximum and CH3 is equal to 2. Okay. And J we have 1, right? 1 and 1 this one because we have 1. 1 group factor. Okay. This one just insert. This one is easy. If you look at here that this one is red color, which is not follow the rules. Red color is not follow the rules. This one we can we call it as we can eliminate. Okay, from the generation of molecule, because if you look at here, even without the Odile Macchiato what is it, rules, okay, we can predict already actually OH is is not stable. Similarly also CH2 CH3 is not stable. Okay, CH2 OH is not also not follow the requirement of the questions. Okay, because the maximum number of OH can present is only once or no OH. Okay, this one is they have a 2 OH. Okay, that's why this one is a red color. Okay, you understand this one? Okay, from this tables we can summarize. Okay, this one, since this one is red, so meaning that this one is not visible. Only the blue color is visible. We can form how many compounds? 1, 2, 3, 4, 5, 6, 7. 7 molecules. So we eliminate 3 molecules, meaning that we can generate from this possible molecules only 4. Okay, understand? Okay, I hope you can understand this one. I think for test, I'm gonna prepare for test 1 for this kind of equation questions. Okay, so I hope that you can understand the how to use the Odile and Macchiato rules. Okay, last semester also this kind of question. Okay, so number of molecule can be generated for a larger set of the functional group. Okay, if you look at here that there are many of the group vectors, CH3, COH. This is definitely for acid. Okay, this is ketone or ketone type or aldehyde type, right? So there's many chemical, million of chemically feasible molecule structure can be generated. Okay, so this one you can just refer. Okay, okay. So let's say we this one is for the molecule structure. How about the mixture blend structure? Okay, so this one I will put in the e-learning. Okay, sorry, I forgot to put in the learning for activity 4 and 5. Uh, I will set it as your assignment 4, 5, and 6. Okay, for assignment 6, I think you have to refer journal. I will provide the journal also because some information we cannot find in your textbooks, so you have to refer the journals, okay, or the list of reference in the textbook lah. Okay, it's already is there actually, so it's from the list of reference in the textbook for the activity 6. Okay, because there's a group of contributions there. You need the informations of the contribution of the group vector. Okay, so activity 6 also actually is we cannot do in the class. Okay, okay, so this one I will set as a for the this one for the assignment. Okay, 4 and 5. Okay, okay, for the generation of the mixture blend structure. Okay, if you look at here, that given a basis set of n molecules determines a mixture containing m max. Okay, m max just now is what is it? M is a number of distinct group in the basis set. Okay, more or equal to with the m and equal to or more than 2 that are stables in liquid solution, meaning that is a binary. Okay, at given conditions of temperature and pressure, where m is maximum of molecule, m is the actual number in the solution. Okay, this is the examples given the molecules of methanol, ethanol, benzene, water, find stable liquid binary and tertiary mixture at 298 Kelvin and 1 atm. This one you need information from the Gibbs energy, excess Gibbs energy, because it's a liquid. Okay, what is the binary mixture, or not binary? I think it's just a mixture. Okay, because you said a liquid binary and ternary mixture, right? Okay, so not only binary but also ternary. So actually, once the answer is maybe methanol, ethanol, methanol, benzene, ethanol, benzene, methanol, water, and methanol, ethanol, benzene, or maybe it's more than that. Okay, maybe methanol, ethanol, and water. Okay, ethanol, benzene, and water is more. Okay, but how can we check this one whether it is stable or not? Okay, we have to use the equation of excess gives energy lah. Okay, so for each mixture to ensure that liquid offers stability, so some criteria must be satisfied for all the composition. Okay, so if you look at here, this is the rules. Okay, the equation delta G over RT lah. So this one should be below than 0 when you do the mixture. So this one is just you substitute lah into this equation. Okay, if you still remember chemical engineering thermodynamics chapter 12. Okay, how to calculate this one? Fugacity coefficient, activity coefficient. Anyone remember? How can we calculate? How can we determine? Siapa dulu kelas saya? Ada tak? Anyone from my class? How can we calculate the activity coefficient? Kalau Sushing kelas saya kan? Low, how can we calculate? Low tak ada situ. Low Sushing.
Doktor.
How can we calculate? Still remember?
Tak ingat.
Aduh. Macam mana? We can use what? Wilson equation. Right. What else? And RTL. Kan? Apa lagi? Unifact. Unifact kita tak fokus lah. Uniquark. Kan? Yang tu kalau software. Apa lagi ya? Wilson. Salah satu yang saya the one that I remember Wilson lah. Okay, chapter 12. And RTL. Margules kan? Margules equation. That's all the equation. Okay. Okay. Okay, so recall back. Sebab because in chapter 11 we have to calculate fugacity. To calculate the fugacity, we have to calculate the fugacity coefficient, right? Okay, fugacity coefficient is the symbol is phi. Okay, coefficient. Okay, so uh, here delta G is the delta gas energy of mixing. Of course, delta G of mixing, right? GE over RT plus XI ln XI. This one. So it should be below than zero. This is I highlighted. It should be below than zero. If more than zero, that means that the liquid phase is not stable. So you have to omit or you have to eliminate. Okay. GE is excess give energy due to the mixings. Okay. And I is the mole fraction of compound I because it's liquid, right? So we use XI. And C number of compounds. How many compounds? Okay, 2 or 3. This one. Okay. We have 2 or 3. Okay, or 4. Quaternary. And then gamma R is the liquid phase activity coefficient of compound I. Okay. So by using this equation, actually is easy to check the binary mixture is can establish the miscibility or not. Meaning that it's stable or not. It can miscible or not, right? Okay. So first, because for the multi-component mixture, okay, first we have to check the miscibility. Okay, it is really important. Okay. So if you're miscible, meaning that is homogeneous lah. Okay. No. This does not form a two-phase. Okay, you have to know. Okay. So this one, the equation is easily checked for the binary mixture to establish the miscibility, right? Multi-component mixture, check first to see the miscibility. Okay. If not sufficient condition, only a necessary condition for the stability lah. So you have to check the equimolar binary composition also. Okay. So we have to follow this one below. Okay. Let's see this, recall back the example for the mixture blend structure. Okay, we have a 6 binary lah. Okay, we can generate more actually. Okay, only 6 lah. Okay, we just choose 6. So which one is not stable or not miscible? Okay, we have methanol, ethanol, methanol, benzene, methanol, water, ethanol, benzene, ethanol, water, and benzene water. So for each pair, an equimolar mixture is tested for the stability. Okay, so what we found is the result. Okay, if you look at here, right, benzene and water pair is unstable. Okay, if you still remember the equation, the previous equation, delta G over, what is it the equation? RT lah. Delta G over RT. Right. So GE over RT times with this one lah. Okay. XI ln X XI. Kan? So if you add this one with this one, so this one is below than 0. Right. Okay. This one also below than 0. This one below than 0, below than 0, below. However, if you add this one, it's more than 0. No lah. So meaning that benzene and water is not stable or unstable. Okay. So for the multi-component mixture, even for ternary, if contain this pair, this is unstable. Benzene, water, and methanol. This one we have to eliminate. Okay. So meaning that we have to reduce. Okay, we have to reduce for the we can reduce the mixture blend structure, the candidate. Okay. Similarly, also for the quaternary lah, right? You can calculate. Okay, because this one number of compound is only 2. Okay, if 3 you have to x1, x2, and x3 lah. Okay, this one is gamma I you can calculate or you can determine from the handbook, engineering handbook lah for each temperature. Okay, so for example, this one is example 6 binary pair for ternary mixture, 1 quaternary mixture, and total is 11 mixture. Okay. Okay. So since the benzene and water is unstable, okay, only 7 liquid are potentially stable and 7 is potentially unstable. We can generate until 11 maximum. This one is just some of the the binary mixture and ternary mixture. Okay, so it's more. Okay, we didn't calculate for the tertiary. Okay, so you can refer to the if you want to read more, you can refer to the example. Example 4.7 unstable binary pair. Okay. Okay, so that is uh, about the mixture blend structure lah. Any question about this one? Any questions? Okay, clear? Clear? So for the binary, for the mixture, the important thing is this one lah. Delta G gives energy of mixing. Okay? Okay, please remember this one. Because for the molecular structure, the important thing is this one, Odile and Macchiato. Okay? Okay. So let's we move to the next part, part 4. Okay. Uh, about the property predictions. Okay, that has a hierarchical for the property prediction or the levels. Okay, that is the important. Before you do the CMD, CMBD problem formulation by using ICAS. Okay, property prediction is important because we need the target properties. Okay, because it also include the pure compounds as well as the mixture properties. Okay, so the selection is important. So which one is more priority and which one is not the priority? So they have how many hierarchy? I think it's a 4. Okay, primary, secondary, functional, and mixture. Okay. Okay. No question. Okay, from the previous slide. Okay, for today I think this is only until the only for the primary lah. Okay. Just very short. And then you have a sometime you can do the activity 4, 5, as well as 6. Okay, you have to do the activity 4, 5 first. Okay, before I upload activity 6. Okay. Okay, for the CMD or CMPD, the target properties usually include pure component as well as mixture properties. Also the selection of properties estimations models to predict uh, uh, there's some additional issue. Okay, like application range, availability of the parameters, like boiling point, right, melting point, all those things, and also uncertainty. If there is uncertainty, you can actually you can remove lah for your prediction. Okay, because it's uncertainty, right? And that's this one if a parameter is not available, okay, so we can remove from the list of candidate this one uncertainty lah, this one. Okay, we eliminate as a potential optimal products. Okay, estimation models with fewer parameters and larger application range are needed. So this one, like you have a thousand candidate, so we have to do the screenings based on the hierarchical. Okay, the primary, secondary, functional, as well as what is it, mixture lah. Okay. Okay, so this one, this is a property arrangement task. Okay, if you look at here, that they have a 4 hierarchy. Okay, the property estimation task, if you look at here, that it arranged in the hierarchically. Okay, based on the computational effort and cost. Okay, so in order to calculate the properties value. Okay, so for example, you have a thousand of candidate, right? So you have to screening based on the this hierarchy. For example, primary, you have to check first the temperature, this one, critical pressure, critical temperature, critical volumes. Okay, and then after this one you can move, and then after that reduce to 500, you move to the next level, next hierarchy. You see the tension, eccentric factor. Okay. Okay, and then if you can reduce more, you can do to the third hierarchy lah, vapor pressure and so on for the mixture. Okay, so from this one, okay, until the end, okay, from maybe just until 100 candidate or 50 candidate, so then you can do the what is it? You can simplify and you can do the verifications and as well as verification by the experimental and also simulation. Okay, this one of course you will do the simulation. Okay, so that is the hierarchy. Okay. Okay, so the classification of the properties we can define from the previous slide, from the previous tables. Okay, primary is the single value properties. This is we calculated using the structure of informations. Secondary is addition to the structural information, right, from the primary. Usually a function of other properties. For example, if we have CH3 CO C and CH3, right? Okay, this is maybe you calculate the primary. See, this one is a primary. This one is a primary. Okay, and then actually is enough only to calculate the primary by using the only the primary lah. There's a question only primary, and then if the value is not close with the actual value, so you can add another equation like a Taylor series to make it more accurate. Okay, so this one is maybe the secondary lah. Okay, this uh, this group. Okay, okay, so you have to define. Okay, okay, and then functional is a pure component properties that depend on the intensive variables, temperature and pressure, while mixture is the structural information. Okay, this one also from the primary. Okay, and secondary depend on the intensive variable, temperature, pressure and composition. So if you look at here, this is the properties. Solubility of course is depending on the pressure and temperature. Okay, okay, so what is the relationship among properties, property models, solver and the calculation algorithm? So if you look at here, if you want to calculate the primary and secondary and the functional as well as mixture, so to calculate the properties we need use the model of Unifact. Okay, EOS SRK. Unifact, this one is for the mixture, right? Binary, right? Marirogani is if you still remember, SRK, software decom equation of state lah. Okay, so this is for the first property model. Okay, so however for the VLE, okay, LLE, vapor liquid equilibrium, liquid equilibrium and SLE. Okay, this is based on the equilibriums lah. Okay, so we need the nonlinear equation and also optimization. This is a numerical solver lah. Okay, however all this one we have to calculate based on the order and also according the hierarchy. Okay, from this one this one the hierarchy. First is primary and then secondary and then third and so on. Okay, so this is important. Okay, so let's see the models for the primary properties. Okay, we see the primary properties first and before we move to the secondary and maybe also the tertiary. Okay, okay, so this is the models for the primary. Okay, so if you look at here, right, property model that employs structure variables are appropriate. So group contribution approach by Marirogani method. This is a simple, accurate, okay, has extensive group parameters, okay, tables for broad arrays of properties and molecules. Some information like a contribution we have to refer to the, if you look at in the page 87, okay, like a group contributions we have to refer to the Marirogani paper lah. If you look at here based on this equation, okay, is the occurrence. Okay, sorry, I think it's the contribution. Okay, occurrence is number of group. Okay, occurrence. Okay, n is occurrence. for the first order group lah. Okay, C is a contribution of the first order group. Okay, and then D is a contribution of the second order group. Okay, with M their occurrence. Okay, this occurrence actually you can find from the paper. Okay, the occurrence, the calculation of the occurrence, not occurrence, the value. Okay, because this one is not standalone. I think it's a new topic in the product design, like chemical and product design. So he did not include it in this text. So meaning that it's not standalone. Okay, and then O also the occurrence. AK is the contribution, group contribution for the third group. Okay, where F theta is the function primary properties. Function primary properties, for examples, like this one lah, boiling point, critical temperature, all those primary properties. Okay, so we can refer to these tables. Okay, normal boiling point. This one. Okay, this is F theta. Later I will explain. Okay, so this is the explanation. C is the first order group type, with N is the occurrence, and J is the occurrence. Okay, O is the occurrence. Occurrence is number of group. If you have a CH3, CO, CH3. How many occurrence? 2C, CH3. CO is only one occurrence lah. Yeah, CH3 is equal to 2. Okay. While for the contributions, we have to see, if you look at here, that we have to refer to the paper. Later I will provide for the activity 6. It's the same. Okay, so it's a very long list for the contribution for each group. Okay, CH3, CH2, and so on. Okay, second order, just like now I've told you, this one we can define maybe is like a ester, right? Okay, if you define as a CH3, CH3. Okay, maybe you can define this one as a second group, but not necessary. Okay, not necessary you have to do second order or third order. So you can start from this one first, only first order. Only first order. The important thing is first order, not necessary for second order or third order. Okay, only necessary. It's like a Taylor series. When you Taylor series is like you do the correction again. For example, the actual value for the experiment is 2.4, and then first order is when you calculate is 4, right? And when you add a Taylor series, this one, another one, maybe minus with 2, so 2.00, almost close. And then third order is plus with 0.5. So when you add the third order, it become 2. This one 0.5, 2.5. It's like a adjustment, right? Okay. So we generally have to verify by the experiment. Okay. Okay. So the main thing is only first order. Okay. What is the number of occurrence and also the contribution. Okay. Okay. So previously I already explained on the right side of the equation. This one, right? How about the left side? Okay. Left side is this one, left hand side. Okay, if you want to calculate the normal boiling point, you have to substitute F theta with this equation. What is it? If you want to calculate the critical temperature, this one. Okay, this one is list only for the primary properties. Okay, and the next part for the secondary. Okay. Okay. So meaning that F theta, if you replace, is become this equation. Exponent TB divided by T, this TB naught. Okay, TB naught equal to is as I told you, the priority is only for first order, right? Number of occurrence, we know. Contribution we can get from the list of table, from the reference, right? So just time you can calculate the TB. TB naught is initial boiling point, right? Okay. Okay. So we can calculate. So in general, step to use the primary properties, first what you have to do is to identify the functional group. Okay, what is the functional groups? Okay, like OH, COOH, that is functional group. If first, and if necessary, this one I highlighted, second and third order group. Okay, if necessary. Okay, it's not necessary, you just use until first order. Determine how many groups of type needed to represent one group. This one, how many group is occurrence? Occurrence just now is n, and I for first order. C is the contribution. Retrieve parameter from the model parameter table for the properties of interest. And this is a contribution. Sum of the contribution and use the corresponding property model function. So meaning that if you have a first order, second order, and then you have to sum all the group of contribution and the occurrence. Yeah? Okay, is it clear? Okay, let's see the example. If you look at here, estimate the normal boiling point, right? Estimate the normal boiling points of butanoic acid. Okay, diisopropyl ester. Okay, so it's given the molecules there. Okay, if not given molecules, this one is generated from the ICAS smile punya smile apa? Let me check the smile. Smile is like smile compound. This is the code for this compound actually. Okay. Okay. So actually from the ICAS we can generate this compound. Okay, it's already have a like a identification ID number. This is the structure. Okay, for the butanic acid diisopropyl. If you insert this one in ICAS, so we can generate this compound. Okay, in the software. Okay. Okay, I think it's from the website Smiles. Smiles. Okay, we can generate also actually. Okay, from the Google's SMILES. Okay, this one. Okay, using the Maragani method and group contribution parameters. Okay, so look at here. Okay, how many first order, second order groups, and third order group? Okay, so we can check lah. Okay, so if you look at here, right, first order, this one. First order CH3, CH3. How many CH3? Only 2. How many CH2? CH2, 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 CH2. 4 lah. CH2, CH2OO. Okay, mana? 1, 2 is 2. So this is first order group. Right. So number of occurrence, this one is 2, 4, 2 lah. Okay, you can calculate first by using equation. It said there's a boiling point, isn't it? So meaning that for the boiling point, the equation is exponent TB divided by TB naught equal to, what is it? Number of compound. Okay, CI. First order. Okay, if you want to add third order, second order and third order, you can add. Yes. Okay. Okay. Is it necessary? Okay, we try this one first. Let's see the answer. Okay. Number of occurrence is from number of occurrence already set. How about the contributions? That one you have to refer in the if you see the example 4.9, estimate a normal boiling point. Okay, in the textbook. So for the group contribution parameter is from Hokuriker et al. 2012. The data is there. Okay, actually it's already we have the value from the calculated and experimental. So we just substitute the C. Okay, if necessary for D, and O you have to put. Okay. So since if the value from the experimental is if from the calculated is far from meaning that not close with the actual value from the experimentals, so you need the second order. Okay. For example, second order here, which one you want to use? Okay, so you choose this one. OCOH3 CH2 CH2C on. Okay, you define this one as a second order. Okay, so you define this one as a second order, only one. Okay, and third order is not necessary. Okay, so when you calculate, if you look at here that the value is close with the experimental when you use second order. So if you use the first order, I think is a much not really accurate with the experimental. Okay. Okay. Any questions about this one? Okay. Okay. Similarly, also for the polymer. Okay, if you want to use this one is a properties polymer repeating unit. Okay. Base method by using a Van Crenen NG method. Okay, adapted from the for the polymer to calculate the glass transition temperature. To actually to see the glass to know the glass transition temperature, we can use like a instrument DSC. Okay, this one how you to predict. Similarly, this is for the primary. Okay, for the glass transitions, it's not mentioned here. There's a note in the tables 4.5. Okay, I think you have to refer to the is mentioned here. Okay, glass transition. Oh, Ghani et al. 1997. Okay, so I think the equation is there. Okay, so if you look at here that once you this already given y, this one right m, so just substitute lah. Yeah. Right. Okay, and then you can calculate the TG. Okay, so you have to refer this one. Please look at the CAPEC property prediction software. Ghani 1997. Okay, so we can calculate the glass transition. This is by using the Van Crevelin's method. Okay, any questions about this one? So is it okay? Any questions before we stop? Okay, so you have activity 6. Okay, uh, the experimental data for the ethyl pentanoic acid is hardly available in the any database. Okay, therefore we need to predict it using available model lah. Okay, estimate normal boiling point, normal melting point, heat of fusions. Okay, using the Marurogani model. Okay, so please refer to Marurogani 2021 paper. This one 2021 paper or 2012 paper. Let me check first this one. Okay, I think it's 2012. Activity 6. Okay. In your solution, clearly show the clear step that need to be followed in predictive parameters. So, meaning that for this one, 2021. Okay. This one I will confirm first. Okay, I think it's 2012. You have to do until only the first order. Okay. So the equation is F theta equal to summation of Ni Ci this one. Okay, to calculate normal boiling point, melting point, and heat of fusion by referring. I think the group contribution is in this paper. Okay. Okay. Any questions? The deadlines before the next class lah, because the next class I want to, I think I will explain a case study about the ICAS lah. Okay, and then after ICAS, model for the secondary lah, this one. And also this one is not really in only one class we can finish this one. Okay, the main thing how to use software and also the case study. Okay, any questions? Ada soalan tak? No, clear, doctor. Okay, good. So you have three.
Doctor,
Huh?
I have a question.
Okay, what?
So at the slide 101, the formula, that one, so we need to calculate the boiling point, right?
Yeah.
But why does this one have like the ln?
Ln, this one from the equation. Exponent, right? Exponent. TB, predict, TB not. TB not at the reference boiling point. Okay. You can get from, it's a reference, you know, right? Reference at 25 degrees 1 bar. This one is at NI, TI. Exponent you bring to here lah. In here, there's a ln. It's mathematical. So TB predicts X. Okay. TB not ln NI TI. Okay. So you can calculate the predict one. Okay. Boleh eh? Is it okay?
Okay, doctor.
Okay.
Yeah.
This is just a mathematics. Okay. Okay. So I think you have to master the primary first. Secondary, I don't think it's just secondary. Is you if you really necessary. No? Okay, I don't think we are focusing on the secondary. Secondary is, I think, is more detail, right? Secondary. If you look at here, that including the delta and what else? Okay. So please do the activity 4, 5, and 6 in your groups. Please submit. Okay, before the next class. At the same time, I give you the video how to use ICAS. Okay, from Dr. Azizul. How to use ICAS. Okay. And then we can discuss only by using ICAS to discuss the case study. Okay, I give you the installer and the agreement form for you to sign. And then after you sign, you have to submit to the in the e-learning. Okay, and then you can install the ICAS. If not possible by this week, maybe during the next class, I will give you the this one, the license or the key. Okay. No more questions. Okay. Anything else? Okay. I will upload all the video. Sorry, I forgot to upload. Okay.